Okay, so what I've decided to do, I'm just going to quickly go through the d orbital stuff. This is what we would call enrichment. Okay, you're not going to have to like know how to do all the d orbital MOs. I get them from Gaussian anyway, you know. But I'll show a few of them and show you how we could still probably see the combination of linear combination of atomic orbitals to get these really strange shapes. But it's not obvious the first time you look at it, because when I first looked at it, I thought, how does this orbital come out of an atomic orbital? So, but then we'll look at the transition moment integrals too of these. So this is the MO theory of D block elements. This would have been probably really helpful in Zoll's class, right? Y'all said y'all did some MO theory in Zoll's class. Um, Budget? Oh, Dr. Gross. Okay. Okay. So we're talking about the splitting of the five equal energy d orbitals on an atom. When you put those in a field, this is called crystal field theory. You put them in a field. That field could be typically an octahedral field or a tetrahedral field, and they'll split different ways. Like in an octahedral field, you have the inversion center, so you have G's and U's, and you typically have a drop in the P. The three of those orbitals will form a P group, and then two of those orbitals will form an E group. Or in the tetrahedral complexes, again, it's a 3 and 2 split. There's no G's or U's. Okay. And so what I did was just to see what Gaussian would do is I made a chromium and I put 6 hydrogens on it. Okay, not that that would be um, necessarily a gas phase molecule, but you can do anything in Gaussian. And I wanted to keep it simple. I just wanted s orbitals on the ligands. So I put 6 hydrogens around chromium, calculated all of the molecular orbitals, and I've displayed them all here. And so you can see all of these from the molecular orbital editor. That's what this view is. You have all of the orbitals, and the negative ones are occupied, and the positive ones are unoccupied. And you said have the HOMO-LUMO gap right there between 15 and 16. The units on these energies are Hartrees, which you could convert to kilojoules per mole by multiplying by 2600, roughly 26. I can't remember off the top of my head. It was like 2600 kilojoules per mole per Hartree. Okay. So a really small gap is still a pretty big gap, because if you multiply that gap of 0.5 by 2600, you get a pretty good sized gap. Okay, so here's our molecule. We see the different. This is again the MO editor. You can put which orbitals you want to calculate in here and hit update, and then whichever ones are highlighted will be displayed. So we can go through this. And this is really nice because this shows us the MO diagrams that we've been dealing with are just the valence electrons. So that's something you really need to take away from this morning's lecture. So here's our energy level diagram and the designations of all of those. Way down here, the lowest first orbital is the chromium 1s, and then the chromium 2s, and then the 3 chromium 2p's, then the chromium 3s and the 3p's, and then we get into the valence electrons. So let's look at all of these. So this is plotted out, the full MO diagram for chromium H6. So this is the core electron, the 1s, and everything else is way up there, okay? And so then if we zoom in up here, let's expand that region. And now we have the 2p and the 2s still not participating in bonding. Does everybody see that? They're so far away from the energies of the hydrogen 1s orbitals, there's no interaction at all. So these are core electrons. And then if we zoom in on that region up there, we get this. We still see no interaction with the 3s and the 3p's. This is exactly what we would expect. We have a 3s orbital on chromium, 3 equal energy p orbitals. If there was interaction, we might see some splitting of those p orbitals, but we don't see any splitting at all. We just see the 3p orbitals. And if we zoom in here, notice we went plus or minus 100,000, then plus or minus 10,000. Now we're plus or minus 3,000. And so we start to see now some interaction, and we see that the d orbitals, that 2 z squared minus x squared minus y squared interacting with the hydrogen 1s's. We have the x squared minus y squared interacting with the hydrogen 1s's. We have the chromium 4s orbital interacting with the hydrogens. We have the p orbitals here. We have the dxz, the dxy, and the dyz interacting here. So we see all of the different d orbitals interacting with the hydrogens. And we're going to go through and look at the pictures of all of these. But what does that tell us? That tells us that for our molecular orbital diagram, this is your take-home lesson, it's always the valence electrons that are bonding. They're the furthest ones out. And so even though chromium, you can see here, it's in period 4, it's the 3d orbitals, but it's still just the valence electrons and orbitals that are interacting. It's the 4s, the 4p, and the 3d orbitals that are interacting with the hydrogens. It's not the 3p's, not the 3s, the 2p's, the 2s, or the 1s. Those are all core in the chromium. So it's only those outer electrons that are interacting. This was just a little video that was nice, or a little email I got based on my video saying that he valued my understanding. So it's a nice third-party endorsement of these notes. So in terms of the symmetries, again, s orbitals are all A1G. We get to and so the 1s orbital is deep inside that ball. So we can't even see the s orbital on the ball and stick model. Then we get to the 2p's and the 2s. So here's the 2s, Millikan symmetry A1G, and the px, py, pz, that's T1u in this octahedral arrangement. And so here, now we can see at least the 2s. The 2s is about the size of the blue ball in that molecule. And then here's the p orbitals. Oh, wait, where's the p orbitals? Yeah, there they are. So you can look how they just barely stick out of the blue ball. So those are the 2p orbitals, really tiny, really close to the nucleus. Why are they so close to the nucleus? Think about how many protons are in the nucleus. So the 2p orbital on a carbon is much larger because carbon only has 6 protons. Chromium has 24. Sucks those p orbital electrons really close to the nucleus. The 1s is really close to the nucleus. In order to stay out of the nucleus for something like uranium, these big elements, uranium and so on, the electron is oscillating at close to the speed of light. So we start to see relativistic effects. I don't exactly know how to calculate those. That's a physics question. Okay, but they talk about the 1s electron in order to stay out, and I don't like to think of it as spinning, right? It's a wave, but it's moving so fast because it's so close to the nucleus. It's such a high energy situation that it's moving close to the speed of light. Okay, here's now the 3s. Okay, the 3s is getting close to interacting with the hydrogens, but it's still 95% surface. It's running out of steam before it ever really gets to the hydrogen. So the 3s is bigger, but still doesn't really interact with the hydrogen. The 3p's, here they are, they're close to interacting. But then when we get to the 4s's and the 4p's, it really starts to interact. So now we're at the 4s. And now it's encompassing the hydrogens, and this one is in phase with all 6 hydrogens. So this is our lowest bonding molecular orbital, and it has A1G symmetry. And there you go. That's what that looks like. Okay. Now there are, if you might be able to see, if we did the Z cut, we would see that there's radial nodes in the 4s. So the s orbitals do have nodes as they go up in quantum number, but they're radial nodes. So the 1s has no nodes, the 2s has 1 node. So the inside's green, the outside's red. And then the 3s has red, green, red. It has 2 nodes, 3 lobes, and so on. So this is the 4s, so it goes, red, green, red, green. Is that right? 4 had 3 nodes, yeah. So this is the 4s, interacting with all 6 hydrogens. So here's the the Z squared with the donut around it in phase with the 6 hydrogens. So the hydrogens on the top and bottom are in phase with the top and bottom of that orbital. The hydrogens around the outside are in phase with the donut. Do you know what I mean by the donut? So this is the dz squared. This is what we would typically draw this orbital by hand. We would have this little donut around the middle. Okay. And so this might be shaded. And we would draw that in an octahedral complex in phase with the hydrogens. So these 1s orbitals would be shaded in phase with the donut part. And then the hydrogens on top would be in phase with that dz orbital. So you can see that the dz squared minus x squared minus y squared is that one shape with the toroid around the middle, the donut, and then the 2 lobes on top and bottom. That's the one we've got here. And then the x squared minus y squared is this one where we don't use z at all. So we use z twice here, 2z squared minus x squared minus y squared, and then 0 z squared plus x squared minus y squared. So everyone is used twice in this set of orbitals. The z is used twice over here and 0 over here. The x is used once over here, once over here, and the y is used once over here and once over here. So that's how they're combined in an equal manner. And those are EG. And then we have the P, the 4p orbitals interacting with 2 of the hydrogens at a time. And so that would be the PZ, the PX, I guess, and the PY coming out. And that's actually showing up in our little MO diagram. This one is actually showing up as the highest occupied molecular orbital, the P's. Now, I can't say that that's 100% true because this is a low-level calculation. I did this with this minimal basis set of STO3G. So I just wanted to get a picture of the orbitals, but I don't necessarily believe these accurate energies or that that's definitely the highest occupied molecular orbital. Then we can look at the next ones. This is the DXY, or XZ, I'm sorry, and then the XY, and then the XZ. Now, why would these be higher in energy than these? They've had the same nodes, so it's not just the nodes. Like, let's compare this one and this one. You see, it's the same number of nodes, right? So it's not that it curves more, that it gives it necessarily more energy. I mean, it's not the number of nodes, I guess, that's indicating that it's curving more. Okay. Look at how this one's not interacting with the hydrogens. And this one is interacting with the hydrogens. So because this one is interacting with the hydrogens more favorably, this has a longer box. Y'all understand what I mean by box, like our particle in a box. So if you increase the box, the energy drops. And so because this is interacting with the hydrogens, it's spread out over a longer distance, so it's lower in energy, so that stabilizes this orbital. Up here, we don't really get any extension of the box. We just have that d orbital, and it's not really interacting with the hydrogens at all. Okay. Then we could look at this one. This is the out-of-phase interaction of that dz squared orbital. Look at the node. It's breaking the bonds here. See, there's a node, there's a color change between all of these, breaking all of the bonds. So that's out of phase with all 6 hydrogens. And this is out of phase with 4 of those other remaining hydrogens. So it's much higher in energy. And then here's the, yes?
So, I don't know 5 electrons plus chromium plus 4s2 3d4.
I'm not finding where you are. Chromium 4s2 3d4. Yes. Okay, yes. Okay, yeah. It should be 4s1 3d6 is what you're saying? Yeah. We also get 6 more from the hydrogens. Yeah, 6 more from the hydrogens. And so what we've done with electron configurations, I finally figured out what you're talking about, the 4s2, 3d4, or 4s1, 3d6, so on. That's the ground electronic configuration for a gas phase chromium atom. Okay. And so this is be a gas phase chromium H6. Okay. And we're not then just stuck with the atomic orbitals of 4s2 and 3ds. We have these molecular orbitals that it's formed. And so it's going to be, we're going to get a whole different set of types of orbitals, like these combinations, and then the electrons will fill up accordingly. Yeah. In what theory? Okay, yeah, yeah. You did not include the 4Ps? That's right. And so that's why I just threw it all into Gaussian and the 4Ps showed up. So I didn't force it to do that, but it's showing the 4Ps are lower than the 3D X, Y, X, Z, and YZ. So the Gaussian may actually be wrong, and these two might be switched, right? So here's your d orbitals, and here's your d orbitals. And so if these are switched, then those electrons will be in those levels, okay, which would be the d orbitals. Okay. But it's, I could see why these p orbitals would be. Um, let's see, do I have pictures of them? Yeah, there they are. Because they have a huge box, right? They're spreading out and containing the hydrogens, whereas these right here do not. Let's see, let's go back to these right here. These do not interact with the hydrogens at all. So these are essentially the atomic orbitals, d orbitals on the chromium. If we allow these to interact with the hydrogens, that box length increases, and so then it drops in energy. So I think this is supported that the two d orbitals that interact with the hydrogens directly are going to drop in energy when they're in phase with the hydrogens. They will go up in energy when they're out of phase with the hydrogens. See right here, they're out of phase with the hydrogens, and so they went up in energy. And so then here we have the p orbitals, and then we have the p orbitals out of phase. So you see this is the p orbital here, which is interacting with the hydrogen, and here there's a node, it's out of phase with that hydrogen. And down below too, there's a node here, because it's out of phase with the hydrogen. So even though that's a long box, because it's interacting with the hydrogen, since it's out of phase, it has 2 more nodes. And so you have a higher curvature, which jumps the energy up. Okay. So what I wanted to see, we go all the way to the top. So here's the 4s out of phase with all 6 hydrogens. And so now it's got nodes in front of every hydrogen, and it's antibonding for all of the hydrogens because there's a node that breaks all those bonds. So we've looked at all of the pictures. Now let's look at the transition selection rules. So our D to D transitions allowed. We have an EG down here. We have T2G up here. What we're going to end up with is a G, light is U, and then a G down here. So before we even get into all of the other things, this U is ruining things, isn't it? So we know just from GU rules that an octahedral complex should not have D to D transitions, an EG to T2G or T2G to EG, because of the GU selection rules. So part of the symmetry breaking idea is that these octahedral complexes, if they were cooled down, and this is an experiment I've always wanted to do as a scientist, but I don't have the money or the equipment to do it, is to take a strongly colored substance in a crystal field like this and cool it down as close to absolute zero as possible to see if the color would bleach out. So I think the color is there because we're not at the ground state. We're in some excited state, and that breaks the symmetry. If you break the symmetry, you lose the G and U rules, and then you have allowed transitions. So I think it's a temperature dependent absorption spectrum, but I don't have the money to do that. And so let's do this, light is T1U, X squared, X, Y, and Z polarized light. So let's see if this is an allowed transition. So T1U times EG, and again, you don't have to write this down, it's all in the notes, but you can see this first one produces T1U and T2U, and then multiplying that by T2G, we get all of these pieces, and therefore it's not allowed. We don't see anywhere in here an A1G. We do see an A1 right here, okay? So if a vibrational mode or something in this molecule broke the octahedral symmetry of the molecule, making it C4V, we'd lose the G's and U's, and this transition becomes allowed. Okay, and that's likely to happen in real molecules. You would have something that breaks the GU symmetry and it makes an octahedral complex into a C4V complex, and you have no more GU symmetry, and boom, all of these peaks are allowed. Okay. So this is easy. G's and U's would show that this is not allowed. What about the 4 P's to the d orbitals? So here we have now T1U times T1U, so the p orbitals are T1U. Now we have 2 U's, so this is likely. When you take T1 times T1, you get all 4 of these things, and I've color-coded this for you. Now we have T2G times each one of these things. So T2G times A1G is T2G. 10 times EG, we get this combination of T1 and T2. G times G is G. Then we have the light blue ones. T2G times T1 gives you all 4 of those terms. And then the last one, T2G times itself, you see the A1G here. So A1G means this is not equal to 0. So this would be allowed. A P to D transition would be allowed. You're shaking your head? No, okay. I thought you disagreed. So it's just a showing that this is about as, this is the most complex one I show in all of my notes, like for the whole semester. So we've made it, we've done it. This is the worst symmetry one we've seen, okay? Because we got 3 T's, and each of those T's is 3-dimensional. So we get, 3 times 3 is 9. So then we have 9 dimensions, and then you bring in another 3 and you have 27 dimensions. So we should be able to add all this up and get 27. So we got 3, 6, 9, 12, 15, 18, 21, 22, 23, 24, 25, 26, 27. Got it. Okay. So the homo-to-LUMO is allowed in this STO3G estimate of chromium hexahydride. Okay. So these coordination complexes, here's hydrated copper ions, so you can do this with water and so on. So you can see these different transitions, whether they're allowed or not. I show you some of the orbitals in a tetrahedral complex. Look at some of these weird ones. This makes sense. This is the S orbital on titanium interacting with 4 hydrogen S orbitals. So there's no controversy there. Pretty easy to visualize. This is just S orbitals, right? But look at this one. This is a weird one, isn't it? It's like, what's going on with that? So this is the p orbital here interacting with some d, x, y business, and the hydrogens out of phase with each other, giving us that crazy orbital. Okay. And here it is at on a different axis, and here it is on a different axis. So we get these strange orbitals. Took me a while to figure out what was being combined to make those. And this is an interesting one. Look at those little donut things. Okay. And there's 3 of those because they're on different axes. And then we have the unused or not interacting with any of the hydrogens, the x squared minus y squared. And so notice in the octahedral complex, this one interacted directly with the hydrogens. In the tetrahedral complex, it goes between the hydrogens and doesn't interact. So we have the splitting of the 3 and 2 and 2 and 3, they switch places if you're an octahedral or a tetrahedral. And we saw that from the crystal field theory. This is just some of the crazy orbitals in phase and out of phase for the titanium. So we do the same kind of thing, showing that this is allowed for the HOMO-LUMO gap. Okay. But what I want to get to is this local bond theory versus MO theory. So that's the next set of notes. So again, both of these are allowed. The D to D transitions are allowed, and so is the HOMO to LUMO gap in the tetrahedral complex. And it's because we don't have that GU symmetry that really helps. And this is also a conclusion that these metal complexes should be highly colored because we have allowed transitions and the HOMO-LUMO gaps are in the visible region. And so we see all kinds of beautiful colors. Okay, so let's go on to the next set of notes, which is, I think, more interesting.